Okay, so we've got 2 sets of notes left, and I broke them up into 2 halves just because normally I found that I can't do this all in one day. So I'm going to do Inequalities Part 1 today, and then tomorrow we'll finish what we don't finish in Part 2. Does that work? So after this, we're done our unit, by the way. So in terms of just a reminder of what's coming up, today, tomorrow, last set of notes. Friday's a work day. Monday, Tuesday are also work days. Hopefully in that time you'll come like really close to finishing your assignment. Wednesday we're going to write a quiz. Because it usually takes people more than a class to write a quiz, I'm going to make Thursday after that a work day. And then Friday next week we have no school, so a short week. And then the week after that I'll give you a couple of study days on Monday, Tuesday, and then Wednesday we're going to write our unit test. And then after that we only have 1 unit left, and we're done math. Crazy.
Local craze.
Okay, before I do this, can I just do a quick review of what we've covered so far this unit? Maybe I won't do that. Huh. How do I stop it from doing that now? Okay. Here's what we've covered so far. I need you guys to know all about graphs and functions. Because what is a function? It's an equation. And hopefully we can use that equation to do something useful like, I don't know, solve a pool shot or whatever it happens to be. Okay. Here are some of the basic type of equation graphs you should know about. One is a straight line graph, which is linear. And you guys first learned about linear graphs, I think in grade like 9 and 10 probably. Okay. Another graph that we learned about in this unit looks like this. This is a quadratic graph. And quadratic graphs can, they always have the parabola shape, but they could either go smiley face, or they could go this way as well. A lot of things that are thrown in the air fit quadratic shapes. Okay. The example in your last assignment was a Mario character doing a quadratic jump. Another graph I need you guys to know about looks like this, the one we just did on the pool question. It's the V, and that's the absolute value. What sort of real-world scenarios fit absolute value graphs? Anything that bounces is a really good example. So pool table, air hockey table. Shodi gave an example last time of a basketball bouncing. That could work. Another example for those of you guys in my physics class, eventually when we talk about light and lasers bouncing off of things, like a laser bouncing off a mirror would be an absolute value graph, if that makes sense. Like, here's a laser going in, bounces off a mirror, comes back the other way. So, the last graph I need you guys to know about, at least this year, is the reciprocal graph, which looks like this. Can one of you guys go grab the door? Thank you. Those are the 4 main graph shapes I need you guys to know about in grade 11. In grade 12, we learn a whole bunch more graph shapes. One of them, you guys in my physics class will recognize. It's the shape of like up and down, which is a sine graph, which is like how periods and pendulums work if you're in my physics class. Most of you guys are. Sorry, not everybody is. Okay. So these are the main 4, though. Does that make sense so far? Here's the thing, though. All of these were equations, where this could be like y equals 3x plus 4. Or this could be y equals x squared plus 5x plus 6. Or this could be y equals absolute value x. This could be y equals x to the negative 1. All of these had equal signs. Life is not always that clean cut, though, that things equal each other. Okay. Let me give you an example. Let's say you're a hockey team trying to fill your stadium up. Okay. I gave an example in in a question on this before. Let's say you have a 10,000 seat arena. It would be awesome if the number of tickets you sold was 10,000. Exactly, right on the dot. That means you're full. But do you always sell to capacity? The answer is, well, no, sometimes you don't. And so what you might say is you'd use an inequality and say that your tickets have to be less than or equal to 10,000. And this sign right here is called an inequality sign. And I think you guys have learned those symbols before, right? And that's my goal today, is to help us learn about how to deal with, whoa. Is that what your slide looks like? Is there like a... This is where we're starting. Okay, so here's my goal today. I want to help us solve not equations, but sometimes we have to solve what are called inequalities, where we don't get to use equal signs, and we have to use these little symbols instead, the greater than or less than symbols. And I hope my preamble made sense. Sometimes in life, things equal each other. Sometimes they have to be equal to that or less than. Like the hockey stadium example. I'd love to sell out the hockey stadium, but if you're the Florida Panthers, they only sell out like a couple hundred seats. So, you know, it could be that or lower. So, do you guys know these symbols? Do I need to go over them, or have you guys learned them at some point in your life and you understand how they work? Greater than, less than? Okay, well, here's what we're going to do today then. Rather than have an equation like x equals 2, we're going to say x is greater than 2. Or maybe it won't even just have one variable. Maybe we'll do multivariable equations. So this is y is less than a whole bunch of stuff. Does that make sense what we're doing today? Yep. Okay, let's try it then. Skip this here. First set of notes I want to just read through here. Equations have solutions. That's the whole point of an equation. If I give you an equation, I might say solve for x, and you say x is 5. Is it possible that there's one solution? Sure. Is it possible that there's more than one solution? Quadratic graphs sometimes have 2 answers. Is it possible that there are no solutions? And that's been the big twist I wanted to throw at you this year, the idea that the answer could be no answers. Okay. But inequalities have what's called a solution set, okay, which includes all of the possible answers. And there's actually an infinite number of answers. Let me show you an example here. Let's say I tell you that x is greater than 0. How many answers are there? A lot. X could be 1. That's bigger than 0. X could be 2. That's bigger than 0. 3. Bigger than 0. 900. So bigger than 0. Then we could get weird and say, well, there's 1.1, 1.2, 1.3, 1.01, 1.001, 0.001. Hopefully you get my point here. As soon as I throw this inequality in there, how many answers are there? Too many to count. That makes sense? Every single valid number between 0 and infinity would count. So we can't actually answer this. So our solution gets shown a little differently. We either use a number line or a solution region. And I feel like you guys might have done number lines at some point in your life before. So let me show you one of those. Okay. Here are some number lines. Do they look familiar? Yeah. Hello. So let me just review this with you in case you don't know this already. If this is x is less than or equal to 0, on a number line, what we do is we put a dot at 0, and this dot should be filled in, meaning that you can actually include 0. And then we draw an arrow pointing the other way, saying everything less than 0 counts. So -1 counts, -2 counts, -3 counts, and every other number in between. Here, if I say x is, this is supposed to be greater than -2. I don't know if you guys can see the difference here, but that circle right there is not filled in. Have you ever been shown that before? This is filled in because it is also equal to 0. This should be not filled in. Filled in. And that's because there is no bar underneath here. So you can't actually include -2. -1.9999999. Sure, go ahead, use that number. But the actual number -2, it's out. Okay. So similar things here. Because this one does not have the bar underneath it, it has an open circle. Because this one does have the bar underneath it, it has a closed circle. Does that make sense? So, how many answers are there? Infinite. For this one right here, the answer is 0, or 1, or 2, or 1.3, or 3.4, or -0.99999. That works. Okay. So your answers are going to be a little bit different. You can't just tell me x is 5 because there's a multitude of answers. So let me show you how to solve something like this then. when we try to answer with a solution set, we do it on a number line. So your answers for this are on a number line. What if I give you something like this then? How do you solve this?
To solve for x.
Solve for x as though it was an equal sign. So pretend that it is an equal sign. So I know it's not, but I'm going to come back to that. How do you solve for x if it was an equal sign? Well, subtract 2x. So x plus 4 equals negative 1. Subtract the 4. Okay. If this was an equality, we'd say x is equal to negative 5.
What do we add? How would we add one?
I'm bringing the 4 the other way though. Because we want to get x by itself. Yeah. Okay. Thanks. You take it. Does that make sense so far? Okay, well it wasn't an equality though, it was an inequality. So this is a huge leap here, but if this side was supposed to be less than this side, x should be hopefully less than negative 5. That's all. You do all the same work you would do with an equal sign, except there's not an equal sign there.
But if you do the math.
Now, let's plot this on a number line. So like, here's what a good number line might look like. This would be like, say, -8, -7, -6, -5, -4, -3, etc. Here's -5. Should it be a filled in circle or an open circle? Good. Open circle. And then this means that x should be less than -5. So every number that way is less than should be filled in. So usually we just draw like an arrow saying that all of the answers over here should work. Yes?
Would we not throw -5 into x then?
But it said it was less than, not equal to. So
Did we just get rid of the equal sign and throw the greater than sign back in?
yeah, basically I pretended it was an equal sign for a little while just to do some work. I just threw the sign back in. We can check our work. Pick an answer that should work. Now, -5 does not work though. Well, 2 would be way over here.
-6, -5.5.
Why don't we go with -6? Should -6 be an answer that works? Okay, let's test it. 3 times -6 plus 4 on this side of the equation would be negative 12?
No.
Negative 14. Negative 14?
Yeah.
On this side of the equation, 2 times -6 minus 1 would be negative 13. Is negative 13 bigger than negative 14? It is. I know 13 is not bigger than 14, but in terms of negatives, negative 13 is indeed bigger than negative 14. So that does seem to work.
Because -5 wouldn't work because it'd both be equal.
And they would then be equal to each other, but they shouldn't be allowed to be. Okay. Let's try another one here. What if we make it a quadratic? Okay, so ignore the greater than or equal to sign for now. That's just getting in the way. Make it an equal sign. So x squared minus 2x equals 3x plus 6. If this was a quadratic, how would you solve it as an equality? Sure, bring everything to one side. Let's go this way here. So go x squared minus 2x minus 3x minus 6. So then you'd have x squared minus 5x minus 6 equals 0. Now how do you solve it? Quadratic formula works. There's probably a faster way if you can factor, though. I bet you we can factor this guy. Nope, not 2 and 3. We need numbers that add to give -5.
1 and 6.
Times to give -6. One's positive, one's negative, though, right?
No, they're both negative.
-6, positive 1. Yeah, I agree with that. -6, positive 1. So x minus 6, x plus 1 which means that x equals 6 and x equals -1. Okay, here's our problem though. You know how last time around I just replugged the greater than sign in there? I can't do that on this one, and let me show you why. If I were to do that, x is just less than 6, and x is less than -1. Let's say I were to plot that. Don't do this. But here's where 6 would be. Here's where -1 would be. If x is less than 6, that's everything this way and over. But if x is also less than -1, isn't that actually the exact same thing that -6 covers? I mean, if you're less than -6, by default, shouldn't you be less than -1 as well? It is actually in between. Yeah. Let me show you how I'd like to show you to do this instead then. So don't do what I just did there. Plot a number line though. So like I did, plot a number line where this is -1 and this is 6. And what we typically do is we test numbers in each section of the graph and figure out whether that section of the graph is actually going to be true or false. If that makes sense. So, say 6 here. Give me a number that is clearly bigger than 6.
8.
Sure, 8. So let's plug in 8 up here. 8 squared would be 64. You'd then be minusing 16. So that'll be 48. And if I threw 8 right here, 3 times 8 would be 24 plus 6, that'd be 30. Is 30 bigger than 48?
No.
Okay, so here's what you'd say then. This does not have answers. So I just kind of put some X's there saying every number bigger than 6 should probably not work. Then pick a number between -1 and 6.
3.
0 is probably the best choice actually. 0 is really easy to work with. But 3 should also work. Let's say we tried 0 though. Let me erase this stuff. So Cole says try 0. 0 squared minus 0 would just give you 0. 3 times 0 would give you 0 plus 6. Is 0 less than 6?
Yeah.
I'd say yes. There are answers in this section here. And then one more section to try. Numbers less than -1. So let's try -2. Just erase this. Okay, so if we were to try the number -2, -2 squared would be 4. 2 times -2 would be -4, but there'd be like double negative, so it really means you're adding. So that's had to be 8. 3 times -2 would be -6, plus 6 would give you 0. Is 8 less than 0? You'd say no. Okay. So here's how I'd like you to display your answer then. On a number line, give me -1 and 6. Open circles, and then everything in between kind of gets filled in like this, meaning that you could have 0, 1, 2, 3, 4, or 5. You can even have 5.5. You can even have 5.99999. But you can't have 6 though. As soon as you hit 6, it doesn't work anymore. Does that make sense? So the difference here, you treat it like an equation, but rather than giving me one answer, we draw a graph to show where all of the answers are. So any answer between -1 and 6 is a valid answer. But I shouldn't put those little lines there because that implies that you can equal those. You guys ever seen it written like this? -1 has to be less than x, has to be less than 6. That's where your answers would be.
Yeah.
Yeah, like a domain. Yeah, Lisa.
So when you have like two answers, that will always be in between the two.
No, it's actually possible if I give you the right example, where, and typically in our course, it's either going to be in the middle, or sometimes your answers are like out here. Sometimes that's a possibility. as we go further on in math, sometimes you get more than 1 point on the graph or 2 points on the graph. So you get like a point here and here and here. So sometimes it ends up being like between these points and then like from here onwards. So it depends on the equations. If you take calculus with me in a couple of years, we do a lot more stuff like that. Okay, let's do this last slide here, and then I think we'll go take a break. But I'd like to skip ahead and let's do this really hard one here instead. Could you guys try this one? Yeah, go to this one. You guys try solving this one without me doing it first. And then after we do that, we'll take a break here. So if you're stuck on what to do first, just pretend it's an equal sign and solve it like by foiling and doing quadratic-y kind of stuff. Making up new words there. Quadratic-y.
What was the negative 3x? Can you just follow the negative 3x?
Yeah, foil the negative 3x into that 2x minus 1. Should I do the first step with you guys, or? Okay, you got it. I'll do it in a few minutes. I'll give you a few minute head start. So, like, this should be negative 7x.
Yeah, I agree.
I believe this does require the quadratic formula.
So I don't think we can factor it in.
No. Okay, what are you going to get? Negative 7x squareds. There's 4 of them right here. And then I need to add 3 over here for 7. And then this side I added 2 more. I got plus 9x. Plus 3. This is the quadratic I ended up with. Anybody else?
Oh my god, I didn't get that because I forgot to the other side.
Okay, so do you have positive, negative, negative then?
Yeah, I got like a negative 3x to like 4, but up to 6, and then went back down to 3. Isn't that how it went?
Did I miss one here? So I got 4.
4x.
Now this I have right here is a positive 3x because it's negative 3x times negative 1. So I have a plus 3x right here.
Yeah. What did you do? Shut up.
That was not
I get it.
I think most people, if they make a mistake when they FOIL this one into this one, they don't make it a plus 3x, they make it a negative. And they forget about this little minus sign right there. Is that the possibility if you have a different answer than me? You do need the quadratic formula though. So find the quadratic formula and get 2 answers as decimals.
I got a really long.
Yeah, they're going to be dumb decimal numbers.
7, 3, 0, 8, 6, 0, 8, 0,
Okay, we'll just go with 0.73. So I got negative 7x squared plus 9x plus 3. So I'm not going to use the quadratic formula. I want to show you guys another trick. What I did is I plotted this as a quadratic, and then I'm going to find where it equals 0. And that should do the exact same thing. So I've got a negative 0.2746. I typed that in wrong. Negative 7x squared plus 9x plus 3.
How did
Okay.
Either
So I got an answer when I did this here of negative 0.27.
Yeah.
Why?
Yeah, what'd you get?
I went wrong somewhere in the report there.
In the quadratic equation.
I think
Let me do that one in a second here. Let me try finding the other answer here.
You got the first one as well?
The other 0.
Oh, it's either got a positive 0.27.
I must have screwed up somewhere then.
And the other one I got was a 1.56.
Yeah, that's what I got too.
Okay, let me actually do the quadratic formula then.
I
So you need to do negative 9 plus or minus the square root of 9 squared,
Wait, negative 9.
because this is your b value here of 9. So it's negative b
Oh, I
plus.
just had the numbers in the wrong positions.
Okay. Minus 4, negative 7, 3, all over 2, negative 7. I just need to use the calculator properly now. Negative 9, add the square root of, what is that, 81 minus 4.
Yeah, I can erase it.
Negative 41.
Minus 4, negative 7, 3, divide by negative 14, I guess. Negative 0.27. Anybody else having issues getting these two answers then? Still not happening, eh? I'll come take a look at yours in a second here. Last thing you got to do then is just plot these on a number line. So on a number line, go with 1.56 right here and negative 0.27 right here. And now we need to pick numbers that are on one side or the other and figure out where answers actually do lie. Chances are it's either going to be the numbers in the middle or it's going to be on the outside edges. So give me a number that's bigger than 1.56.
1.57.
How about a whole number?
2.
2. Okay, you're not wrong, but 1.2 makes more sense. All right. If I plug 2 in over here, this is going to be complicated. I'm going to erase some of this stuff here. We'll take a break after this, by the way, guys. All right, so let's say why don't we plug in 3? Okay. 3 times 3 minus 2 would be, that'll be 1 times 3, so this would be 3. And then this would be 4 times 3, so that'd be 12. 12 plus 3 would be 15. Here's where this gets weird then. 2 times 3 right here would be 6, minus 1 would be 5. And then 3 times 3 would be 9, but it would be minus 9 times 5. So it would be minus 45. And then 15 minus 45 would be negative 30. Is 3 bigger than negative 30?
Yes.
I would say yes. So based on that logic, I believe that these answers over here should be true. Give me a number between negative 0.27 and 1.56.
1.
That works. 0 is also good.
But you can't do 0.
Huh?
Oh, yeah, you can.
These aren't reciprocals. I agree with you. If it's reciprocals, you can't use 0. You're right, though. One's not a bad number. I can do 1 pretty easily in my head here. So, okay, this will be 1 times 1 minus 2, so that'll be negative 1. This will be 4 plus 3, so that'll be 7. And then this will be, let's see, this will be 2 times 1, which will be 2 minus 1, so that's a 1. And it'll be minus 3 times 1, so that'll be 7 minus 3, which will be 4. Is negative 1 bigger than 4? Okay, so that means the middle section should not have answers, so don't put anything there. We should just double check and make sure that these numbers work as well. Sure, negative 2. Just one quick check and then we'll go for a break. So negative 2 bracket negative 2 minus 2 is going to give you negative 4 times negative 2. So I got that as being an 8. Oh, this side's going to suck. 4 times negative 2 will be negative 8. Plus 3 means that this stuff will give you negative 5. Okay, throw a negative 2 in here. 2 times negative 2 will be negative 4. Minus 1 will be negative 5. And then 3 times negative 2 will be negative 6. But then with a negative makes it positive 6. And then positive 6 times negative 5 is like a negative 30, I think. So is 8 bigger than negative 35? And I'd say yes, it is. That was a mess. So last thing then, go back down here and say that you can include this number, by the way. And every number smaller than it works. So then if I were asking you the domain, you'd say this. X has to be less than or equal to negative 0.27, and x has to be greater than or equal to 1.56. So those are where your answers are. And there's a lot of answers then. Okay, here's where we're going to go after our break. After our break, we're now going to do things with x and y, and then we're going to start getting into word problems. Because ultimately, we actually have to make this useful to real life somewhere. So go take a 5-minute break, come back at 3, and we'll finish the rest after 3 o'clock. Careful. Resume. Okay, so here's the last, 4 slides? Not much left. My goal now is to teach you how to extrapolate the whole idea of greater than or less than type signs and use them to help solve eventually a word problem. Okay. We're going to do 1 word problem today, and then tomorrow we're going to do 3 more word problems. Does that make sense? Okay, before we do that though, the last thing we have to do is, what if we don't just have x? What if we have x and y? Okay. Inequalities could have 2 variables. That means that your solution set could be ordered pairs. Let me give you an example here of something different first. I don't know why I'm always doing this. Let's say we were working with graphs, and we had a graph, and we had a graph, and I asked you to intersect them. Where they intersect is where they equal each other. That's where this graph equals this graph. And that could be at, say, the point like 18, 24. Okay. That means that when y is 24, x is 18 for both graphs. But what happens if we're dealing with inequalities? What if it had to be less than? It's possible that this could be an answer, and this could be an answer, and this could be an answer, and this could be an answer. But this one up here, not an answer. Because what's happened here is this graph right here, we might have needed points to be less than this line, but we might need points to be bigger than this line. So anything in this section here might actually be a valid answer. But points out here or here, they don't work. So rather than having 1 point work, you actually have points that you're looking for. Sean.
When it says equal to, does that mean that points along the lines could be?
Yeah. When it's equal to, then points on the line would actually count. And then if it was just like less than or greater than, then you couldn't actually count points on the line. So based on that then, sorry this is all smaller now, here's what we do for xy value ones. We do something called reverse shading. Okay. Have I ever shown in your calculator how you can actually get your calculator to shade half of a graph? Done that before? Grab your calculator, I'll re-show you in case you don't know. Go to y equals, if you can get this to work here. And why don't we put in the graph of y equals x, just to keep it simple. Okay. And then go like zoom 6 and just get like a standard straight line graph. If you were to go back to that y equals and go backwards this way, you can change it so that the line becomes like a thick line. And if you keep going further, you might get to one that looks like this, where there's like a triangle there. If you graph that, what this does is it finds all of the points that are below that line. Go to y equals, and do you see how this thing back here is no longer a straight line, it's a triangle? This is going to find all of the points below that line. And you see how everything on the below side of the line is now shaded? Or if I go back to y equals, and I go one further, you get a triangle. Oh, where is the one above the line? That's why. Then if you do the other triangle, it finds you all the points that are above the line. Okay?
Yeah.
These stools are dead.
Yeah, they are. It's kind of landmines everywhere for you to run into. Okay, does that make sense? You guys seen that before, how you can shade your graphs? Now you have them? Okay. We do something called reverse shading. Here's how reverse shading works. The black section of your graph, is where the answers are not. So the answers that are actually true are in the non-shaded section of your graph. So in this picture right here, where are the answers? The answers are in the middle. These are where the answers are. So these are actual answers. And the blue section is not answers. That's typically the convention we use in math, and I'll try to show you why later in a little while. But the idea is we try to shade where the answers aren't. Actually, maybe I'll show you why we do that right now. Let me make a new graph here. Let's say I give you a graph and I ask you to shade this line. Let's say we want everything above this line. So this is where the answers are. What we would then do is we would shade everything below the graph and say this black section down here is where the answers are not. Here is where the answers are. Let's say we had a second line like this. And let's say the second line, we wanted all of the answers below this line. That means we would then shade the sections above. Then my question is, well, where are the answers that are both above this line and below this line? And you'd say, they're over here. And so it often works better to shade where the answers aren't, because then the little section that is not shaded, that is where the actual answers are. Does that logic make sense? Okay, let's try an example then. Whoa, what did I just get open here? No. Okay, so we're going to try to shade where y is going to be less than 2x plus 1. So first thing we got to do is figure out what 2x minus 1 looks like as an equation.
Wait, you said plus.
2x plus 1, right? Sorry. I can make mistakes. Okay, so 2x plus 1 would look like that. We want where everything is less than that. So we want the answers on the lower side and not on the top side. Does that make sense? So we should probably be shading in the top side. I'm just going to sketch this graph here real quick just to make sure we did it right.
It isn't working for some reason.
So there's our graph. And we want to shade where this is, sorry, am I saying this wrong? We want where y is bigger than this. So we want the top side of the graph where the answers are. So then we should be shading the lower side of the graph where the answers are not. I hope this works now. Let's pick a point just to test and make sure this is true. Here's a point right here. Here, x is 1 and y is 10. Would you guys agree with me that this point 1, 10 is definitely in the unshaded section of the graph?
Yeah.
Let's make sure it works. If I put 10 in for y, is it going to be better than 2, 1 plus 1? Is 10 greater than 3? Good. What if we were to pick some of these negative values? What if I picked a value like way over here? This guy would be negative 9, negative 3. Let's just check that one. Negative 3, is it going to be greater than 2 times negative 9 plus 1? Is negative 3 bigger than negative 17?
Yes.
It is actually, because of the negatives. So basically everything on this side of the graph is an answer. Everything on this side over here that I've just kind of shaded in, and by the way, that's all I need for shading in. I don't need anything special. These are where the answers are not, but everything on this side of the graph is where the answers is. Answers is not. Usually to figure out what side to put it on, it's good to just test a point and just see whether that point is on the right side of the graph or not. Let me do this on the next one, because the quadratic ones are harder to figure out. So why don't we do this one next? Here's a quadratic one. We want to figure out where y is greater than x squared plus 3x minus 4. So first, let's just figure out where that graph goes. So this would be x squared plus 3x minus 4. Let's say you're stumped as to which side to shade. Either you're going to shade everything around the parabola, or you're going to shade the inside of the parabola. But let's say you're stuck on which side to shade. Pick a point that is either on one side or the other and test it. We call this a test point. The best test point I can think of is right here at 0 and 0. So I'm going to plug in 0 and 0 and just see whether that should work or not. Is 0 going to be greater than 0 squared plus 0 minus 4? Is 0 bigger than minus 4? Okay. That means that this point should be an answer. So I want to shade the other side of the graph where the answers are not. So then I'll shade all of this stuff. And I could test other points if I want. Let me find another point that is... Actually, why don't I pick a point that I clearly know is wrong, and let's just prove that it's wrong. How about this point down here? This point would be at 10, negative 10. Let's just make sure that that point is clearly not true. Is negative 10 greater than 100 plus 30 minus 4? No, negative 10 is not going to be bigger than something that starts with 100. So clearly this is where the answers are not. That makes sense? Okay, one last example then. Now we got to actually figure out how to make this into like something purposeful. So I want to show you guys one word problem today, and then we'll do 3 more next day. So here's a scenario. What was that? Okay, here's your scenario. You're a baker. As this baker, you have 2 options for making cakes. Option A, you make chocolate cake. Chocolate cake apparently takes 150 grams of flour. Vanilla cake, though, only takes 75 grams of flour. Here's your issue, though. You have only 2.25 kilograms of flour. Do you guys know how to convert kilograms to grams? Times by 1,000. So you actually have 2250 grams of flour total. Here's your problem then. If you want to try to make chocolate cakes are yummy, but they take more flour. So can you make as many chocolate cakes as vanilla cakes? And the answer is, well, no. You could make a lot of vanilla cakes, but maybe you can't make as many chocolate cakes. Here's one more issue. Do you have to use all of your flour? You don't even have to use all your flour. You could make 5 cakes, or you could make 4 cakes, or 3, or 2, or 1. And so our goal now, I've got 4 questions for us to answer here. First one here, let's define some variables as x and y. Okay. I think I need to just do the first one for you. Okay. X, I'm going to define as cake number 1, which I'll call that chocolate. So you could make some chocolate cakes. Or y means you could make cake number 2, which I'll call that one vanilla. So x is how many chocolate cakes you can make. Y is how many vanilla cakes you can make. Now I want to write an inequality to represent this scenario. Let me show you the inequality. A chocolate cake takes 150 grams of flour. So 150 grams times however many chocolate cakes would be here. A vanilla cake requires 75 grams of flour, but you only have 2.25 kilograms. This would be your inequality. Let me see whether I can explain it now that it's written out. You can make some chocolate cakes. 1, 2, 3, 4, 5. You can make a whole bunch of chocolate cakes if you want. But each chocolate cake you make takes 150 grams of flour. Over here for y, you can make some vanilla cakes. But each vanilla cake you make requires 75 grams of flour. By the way, could you make some of each? You could make some of each. Okay. Could you make 17 of one and 47 of the other? Probably not. Why? You're going to run out of flour. Does that make sense? And so now, once I've done B, which is create the inequality, now I'd like to actually graph this thing and talk about the solution set. How do I graph this sort of equation? Get rid of the inequality, make it an equal sign. So go 150x plus 75y equals 2250.
This has a couple of answers then?
This one actually has infinite answers because you could make 1 chocolate, 1 vanilla, 2 chocolates, 1 vanilla, 3 chocolates, 1 vanilla, 4 chocolates, 1 vanilla, 5 chocolates, 5 vanilla. I mean, there will be a breaking point though, right? Where you probably can't make 10 chocolates, 20 vanilla because you run out of flour. So, how do I rearrange this as something I can type in my calculator? Well, it's actually not a quadratic. It's linear because there's no x squared. What did you say though?
Subtract this from the flour.
Get y by itself.
Oh.
Get y by itself.
Okay, subtract 150.
Okay, so subtract 150
Divide out 75.
and then divide it by 75. So doing this in steps, 75y will equal negative 150x plus 2250. When you divide by 75, make sure to divide everybody by 75. And so your equation will be this. Y equals bracket negative 150x plus 2250, all divided by 75. That's what we're going to graph in our calculator. Bracket negative 150x plus 2250 divided by 75.
Yeah, would you not put a graph?
A bracket. Okay, well we need to change our window size. Because x is about how many cakes you can make for chocolate, and y is how many vanilla cakes you can make. And you can probably make a lot of chocolate and vanilla cakes. So I'm going to suggest we change our window size. First thing here, can we make negative cakes?
No.
Start at 0. For both of them. You probably could make more than 10 cakes with how much vanilla you have. And how much flour you have. So I might suggest let's go from 0 to 30. And 0 to 30. I'm just picking a number out of nowhere. Here's the graph.
It isn't.
Wanna take a look? Okay. Okay, let's talk about what this graph means then. Just about done. Just bear with me.
Is that just how, like, how much you're running?
Okay, X was defined as how many chocolate cakes you can make. Chocolate cakes. Y was how many vanilla cakes you can make. And here's your graph like this. It wasn't a fantastic graph. Sean.
Will that be like whatever point on that line will be how many chocolate and vanilla cakes you can make?
Well, this would be the most you could make.
Yeah.
Okay. Like my next question was about what the y-intercept is. The y-intercept here is really saying how many vanilla cakes could you make if you made no chocolate cakes? What'd you get?
30. Right on the dot.
Okay. So what that means then is you could make no chocolate cakes and you could make 30 vanilla cakes. You have enough for 30 vanilla cakes. And then your x-intercept. Anybody found that, by the way?
I'm finding it right now.
Thank you.
15. It should be exactly half.
15? That's a good point. It should be exactly half, shouldn't it? So here are some options. You could make no chocolate, all vanilla. Here you could make all chocolate, no vanilla. But there's more possibilities. What about this possibility right here at, say, like 2, 2? Could you make 2 vanilla, 2 chocolate? Did anyone say you had to use everything for flour? No, they just said that you couldn't use more than the 2.25 kilograms you have. So every point inside here is all a valid point. So then you'd say, this you can't do. We're shading this side right here because this is the side of the graph in which you're making more cakes than you have the ability to make because you don't have that much flour. So, I mean, this point right here, you could make some chocolate, some vanilla. You could make some chocolate, some vanilla. Give me one more second here. There's one more point that's really important here. This point right here at 0, 0. Could you do nothing? That is a valid parameter. As a baker, you could make no vanilla and no chocolate. That is valid. Could you, however, do -2, -4? You can't make negative cake, but you could do nothing. You could make 2 of each. You could make 8 and 12.
The students from the career fair are back in the school and they need to return to class, please. I have messages for the end of the day for Brandon Creighton, Logan Marsh, Mercedes
Sorry,
Smith,
you had a question, Brianna,
and
that I
Sienna
was
Crowshoe, please.
Yes. Yeah, let's say that louder for everybody to hear. Anything that is on the line then would be using all of your flour. And that's a valid possibility. You could use all of your flour. So like, for example, if I go to my table of values, you could do 0 chocolate, 30 vanilla, 1 chocolate, 28 vanilla, 2 and 26, 3 and 24, 4 and 22. These numbers would be using all of your flour. But you could do points in the middle here, which just means you have leftovers. So let me go back to my initial premise here. When you do inequalities, how many answers are there? An infinite number of answers. So as a way of showing it, we do a graph and we shade where the answers are not. Therefore, any dot inside this section right here is where an answer is.
So you could do like half of the vanilla cup?
Sure, you could do half a vanilla cake and 2/3 of a chocolate cake, if you really wanted to even. So you could even use half numbers. Does that make sense?
Yeah.
Okay, one last thought, then you guys can take off, okay? These questions are going to be very different than the previous questions you give. Your answers will not be concrete answers like saying the answer is 7. Your answer will be a picture, a graph. And your answer will basically be anything inside of here is a valid answer. Often what I do then is I ask you to give me some examples of valid answers. So like you could say 2 and 2 works, 8 and 12 works. You could say 15 and 0 works, or 0 and 30 work. Okay? But all of those are answers, so your answer is really a picture. Just kind of different than normal. That makes